Alright, so here we have the fundamental theorem of calculus, part 1. If f is some function, and it is continuous on the interval a to b, so f is some function that's continuous on some interval from a to b, and capital F represents the antiderivative capital F represents the antiderivative of the function f on the interval ab. Then, if you want to find the area under the curve from A to B, you can simply plug B into the antiderivative, get that answer, and subtract whatever you get when you plug A into your antiderivative. So, you had a problem on your first quiz where you wanted to find the area under the curve of f of x equals x squared plus 2 from -2 to 2. And you had to do that using Riemann sums. Riemann sums, remember, was when we broke up the area under that curve into an infinite number of rectangles and added the areas of all those rectangles together on the limit of the area. Okay. Well, the fundamental theorem of calculus says that if you want to find essentially the area under the curve of this function from here to here, all you need to do is set up your antiderivative from -2 to 2 of the function.
Wilson and Jeremy Frame, please report to Miss Martin's room. Jeremy Frame and
the way we usually write this,
please report to Miss Martin's room.
Is we do the antiderivative of the function. So what is the antiderivative of x squared plus 2?
1/3 x cubed plus 2x plus c.
1/3 x cubed plus 2x. And then plus c. Now I'm not going to write that because if you think about it, whatever c is, okay, let's say c is 10, okay, for instance. When I go to plug 2 into the antiderivative, even if there was a plus 10 back there, when I go to subtract out the answer when I plug in a -2, won't we subtract that 10 right back out of there? Because again, what am I going to do? I'm going to plug this top number into my antiderivative, get that answer. Then I'm going to subtract whatever I get by plugging the bottom number into my antiderivative. So even if there is some constant back there, I'm going to add it and then I'll subtract it. So I'm not even going to worry about it. Because they're going to cancel each other out. You with me? Okay? And then what we usually do is we just usually make a vertical line here. This is usually the notation that you'll see. And you'll put the top number up here and you'll put the bottom number right here. Just the notation that we like to use. So then what I do is I take the top number and I substitute it into my antiderivative. So 1/3 times 2 cubed plus 2 times 2. I'm going to get that answer. And I'm going to subtract 1/3 times -2 cubed plus 2 times -2. So again, I'm going to get the answer by plugging in the upper limit into my antiderivative minus the lower limit substituted into my antiderivative. 2 cubed is 8. 8 times 1/3 is 8/3. 8/3 plus 4, that'd be plus 12/3. So 8/3 plus 12/3 is 20/3.
Could you just cancel out like the first term over there and first term over there? Do you end up equaling the same thing?
This is -8/3.
Negative 8. Isn't like
Because -2 cubed is -8. -8 times 1/3 would be -8/3. So -8/3 plus -4. Okay? So that'd be -20/3, right? So 20/3 minus a -20/3 would be 40/3. Or 13.3 repeating, like you guys that did the answer, or got the answer correct on your quiz, found your answer to be 13.3 repeating. Or some of you left it as fractions, 40/3. But now you were able to find the area under that curve without using Riemann sum, without finding the area of all those infinitely small rectangles. And here is the fundamental theorem of calculus part 1 in action right here. So if you know the velocity, I'm going to apply this back to physics a little bit. If you know the velocity of something over a period of time, okay? So if you could create some function that represents the velocity of an object over a period of time, and you want to know how far that object traveled, whatever this function is, you'll just do the antiderivative of that function. Plug in the value at the far right that you're concerned with, minus, plug in the value at the far left. That'll find the area under the curve, which is the distance that that object traveled. So a little bit of application as to where this can be applied. Right? Let's do one more just for the heck of it. It's actually one off your practice. Find the area under the curve from 1 to 8 of the square root of 2 over x. First of all, is the function continuous from 1 to 8? So I guess if I plug in a 1, 2, 3, 4, 5, if I plug in numbers between 1 and 8, I mean, is this function always defined? Will it be a nice continuous function?
Yes.
Yes, it is. Okay. So as long as it's continuous, you can follow the fundamental theorem of calculus rule. If something is not continuous, though, you would not be able to find its area under the curve. Okay? To do the antiderivative, what would you do?
change it to
Rewrite it?
yeah.
Yeah. What would you rewrite it as?
2x and -1.
Or just do
2 to the half, and then x to the negative half.
Yeah.
Because really, both of these are being raised to the half power, right? You have 2 to the half power over x to the half power. So I'd probably write it as 2 to the half power times x to the negative a half power times dx. You want to move that constant out to the front too? So you don't have to mess with it?
Yeah.
I would. So I have 2 to the half power out in front. And the antiderivative from 1 to 8 of x to the negative 1/2 dx. Antiderivative of x to the negative 1/2.
2x to the 1/2.
That work? Well, it's 1/2 times 2. 1, and then x to the negative 1/2. So, yep, that looks good. And we're going to evaluate that function from 1 to 8. So I have 2 times 8 to the half power minus 2 times 1 to the half power. See how good we are. Simplifying. What's 8 to the half power? Square root of 8. Simplify.
2 point.
No, not decimal. Simplify the radical.
Oh, 2 square root 2.
2 root 2. Okay. This is 2 root 2 times 2.
4 root 2.
So that's 4 root 2. I'm going to change that to this root 2 out in front here. 2 times 1 to the half power, which is just 4.
2.
What's 1 to the half power?
1.
1 times 2 is 2. This is 4 root 2. That's 2. These aren't like terms, but I'll go ahead now and distribute. Root 2 times 4 root 2.
8.
8. Because root 2 times root 2 is root 4, so I'd have 4 root 4, but root 4 is just 2. So 4 times 2, that'd be 8. And then root 2 times negative 2.
Negative root 2 root 2.
Minus 2 root 2. So the area under this curve from 1 to 8 would be 8 minus 2 root 2. You're going to have to show your work, but you are able to do these on your calculator as well. So that was the square root of 2 over x, right? So here's the graph of the function. If I go to second trace, which is calculate, which is right up here, number 7 down there, you see it? Antiderivative. We had a lower limit of 1, right?
Yeah.
And an upper limit of 8. From 1 to 8, it kind of colors it in there for you. 5.1715. Okay, I will not accept that decimal, but what was it? 8 minus
2 square root of 2.
way to check your work. Okay? So you can check your answer using the graphing calculator, but there's kind of your first example of what's called the definite integral, or using the fundamental theorem of calculus to help you find the area under